scalar product or dot product of vectors. So let us consider, okay? Consider vector A and vector B. So we have vector A and vector B incline at angle theta. So let theta, okay, be the angle between vector A and vector B. Now, the scalar product or dot product of vector A and vector B is given by vector A dot vector B. So this is called the scalar product or dot product, and this equals magnitude of vector A, magnitude of vector B cos theta, or we can simply write in this way, AB cos theta. Let us call it equation 1. So this is equation 1. Okay. So equation 1 gives the general form of scalar product or dot product of two vectors A and B. And we need to note, okay, that both vector A and vector B have direction, okay, but their scalar or dot product, so I'm simply writing in this way, that is vector A dot vector B have no direction. So this is to be noted, okay. Now let us consider this case, okay. If cos theta is associated or is taken, okay, so I'm writing in simple way, if cos theta is taken with B, okay, then equation 1 can be rewritten in this way, okay. We have A and bracket B cos theta. So we have this. Let us call it equation 2. Now we need to understand, okay, equation 2. So for that, let us take or draw coordinate axis, okay, in this way. So this is y and this is x. So vector A is along x-axis. So we have this. Clear? And what we find, the tail, okay, the tail of both vector is at origin. Okay, so we have this. Now from the head, okay, this is the head. So this is also the head. Okay, so from the head of vector B, so from the head of vector B, drop perpendicular on vector A. So let us drop perpendicular. Okay, so we have this, and this represent the foot of perpendicular. Now this length, okay, this length represent projection of vector B on vector A. So we have this. So this is to be noted, okay, and this projection, okay, this projection equals, or it is the x component, okay, of vector b. So this is the x component, okay, it represents the x component. So this, okay, gives the x component of vector b. Clear? So this is to be noted. Now let us find cos theta, okay, in this triangle. So cos theta, we know cos equals base by hypotenuse, and the base is projection of vector b on vector a, which is the x component, okay, of vector b. So cos theta equals bx, and the hypotenuse, okay, this distance is the hypotenuse, so I'm writing in magnitude, okay, in this way. So cos theta equals bx by magnitude of vector b. Therefore we can write bx equals b times cos theta. So we have this. Clear? So we can write in this way, okay, vector a dot vector b equals, this is, okay, the magnitude, this is the magnitude of vector a. So if you look into this expression, equation 1, okay, we are taking vector a as a first vector. So we can also write magnitude of a or magnitude of first vector. So we can also write in this way. Clear? If you look into this expression, equation 1, or if you look into equation 2, we are taking vector a as the first vector, and we are taking vector b as the second vector. And b cos theta, okay, what is this? This is projection, okay, projection of vector b on vector a, and we know bx equals b cos theta, okay. So we have this, or we can also write in this way, okay, the scalar product or dot product of vector a and b equals magnitude of vector a or first vector, okay, times, okay, this is what? This is the magnitude, okay, we know it is bx, clear, the magnitude of component of vector b in the direction of vector a. So magnitude of component of vector b in the direction of vector a. So we have this. Now if we take, okay, cos theta with a, then from 1, okay, we can write vector a dot vector b equals, I'm keeping inside bracket, okay, a cos theta b. So we want to, okay, so let's call it equation 3, and in previous case, okay, if we take cos theta with b, so we had done this, then we can write in this way, okay. So this was equation 2. So we have this. Now let's understand this, okay, equation 3. Now I'm taking the same, okay, figure or diagram. Okay, so initially we had this. Now what we do, clear? If you see the previous figure, okay, then vector A was along the x-axis and we had this y. So this was for this case. Okay, now what we do, we rotate the coordinate axis in such a way that now vector B is along y and we have x, okay, in this way. So we have this. So we rotate the coordinate axis, okay, in such a way that y and vector B, okay, they are in the same line. Now this is the origin. So we find tail of both vector is at the origin. Now let us drop, okay, this is the head. Now let us drop perpendicular from head of vector A on vector B. So this length, okay, this length gives the projection of vector A on vector B, okay, and this projection represent the y component, okay, this represent the y component of vector A, clear? So if we move from the tail to this point, okay, in this direction, then this length represent the projection of A on B, which is the y component of vector A, okay. So we have this, and let us find cos theta in this triangle, okay. So cos theta equals, and we know cos is base by hypotenuse and base is AY and hypotenuse is this length. So it is the magnitude of vector A. So we have this. Therefore, we can write AY equals A cos theta. So this is to be noted, okay. Therefore, we can write vector A dot vector B equals, so what is this? This is projection, okay. This is projection of vector A on vector B, and this is, okay, magnitude of vector B, or what? It is magnitude of second vector. So this is to be noted, okay. And this A cos theta, okay, which is the y component of vector A. So this is the magnitude, okay. It is the magnitude of component of vector A in the direction of vector B. So this is to be noted. So what we do is that, okay, the scalar product, okay, so I'm writing over here the scalar product of vector A and vector B is A, and we have B cos theta, or we can write in this way, okay. And in general, we can write this. So this is to be noted.